Scientists use a variety of approaches when mapping malaria. Here we will highlight three: suitability analysis, Bayesian geostatistical analysis, and geocomputational biological analysis. Suitability analysis is a spatial decision-making process that evaluates and ranks geographic locations based on how well they meet specific criteria related to a particular purpose or activity. The technique typically combines multiple data layers, such as slope, land use, proximity to resources, or environmental factors, using weighted overlays to identify the most appropriate locations for objectives like site selection, conservation planning, or resource allocation. Suitability analysis focuses on mosquito population ecology, or the interaction between the mosquito and the environment. In 1999, Craig et al. Used suitability analysis to create the first continental scale map of malaria risk by identifying areas with the environmental conditions necessary for disease development and transmission. This model identified areas where temperature and precipitation remained favorable simultaneously at least 5 months, the minimum time needed for stable malaria transmission. Malaria can also be mapped using Bayesian geostatistical analysis. Geostatistics is a subfield of statistics that incorporates location data and spatial autocorrelation into predictions about the magnitude of phenomena at unmeasured locations. In 2007, Hayes et al. Used this statistical method to predict the prevalence of malaria cases worldwide using case data collected in multiple regions. The resulting Malaria Atlas project has produced global estimates of malaria cases dating back to 2000, which allows researchers and public health professionals to visualize disease patterns across space and time. This approach focuses on human-parasite relationships in the malaria lifecycle and is an essential complement to suitability analysis. Malaria can also be mapped using geocomputational biological analysis. In 2013, Blanford et al. Furthered the suitability approach by using the results of laboratory experiments to predict where malaria was likely to occur based on the interaction between the mosquito and temperature. This creates more precise monthly malaria risk maps, and the method helped explain why malaria sometimes occurs in areas previously thought too cool for transmission. By using more precise temperature measurements that better reflected mosquito microenvironments, this approach revealed why malaria transmission sometimes occurs in unexpectedly cooler areas. Considering these different approaches demonstrates how malaria mapping has evolved from theoretical predictions to data-driven reality.